It has started recording. Okay. So today we'll be starting off with matrices. Uh, we'll be seeing any the questions you raise as scientists and engineers are often solving multiple linear equations. So that led to the introduction of what is called linear algebra, which is a generalization of a system of linear equations. Linear equations. It would have been great to have more people to interact, but okay, we will only have these many. So, but see, what we'll be doing is we will be first laying the foundation of how to introduce matrices. We'll be introducing matrices, how they were derived, and then we will be today seeing what are vector spaces on which these matrices operate, right? So all this operation of vectors and matrices are happen on vector spaces. So for this, you need just the prerequisite of class 11 and 12, knowing how to multiply matrices and add matrices. Other than that, there's nothing that you need to do. So in case my voice is not audible, you interrupt me because I'm not sure if no one interacts. Okay. So given, say, for example, we have this system of equations, right? So given this system of equations, what can you say about the solution? So there are many ways you can solve it algebraically. You can solve it the way you used to solve in middle school, right? So by drawing the graph. So x plus y equal to 1 is this, right? If this is 1, this is 1. This is your x plus y to 1 line, right? So you can write these as lines, equation of lines. Similarly, x equal to y is equal to this line, right? So if these are the two lines, they meet at this half comma half. Do you agree? I hope you see that if you see the intersection of these two lines, they will meet at half comma half, right? This is what you did in school. But today we'll be seeing how can we solve the same question using vectors. So how will we be using vectors to solve the same question? So what will we be doing? See, so we will be changing this set of equations into a vector. So can I write this in this way? In form of matrices? In form of 1 minus 1, x1, x2 equal to 1 comma 0. Can I write this? So this is all I'm writing is I'm combining these two equations into a single equation. I can write this, right? So this is a simple vector equation. So in case you don't follow, please interrupt. So once I do this, can I say this is a vector 1 and this is vector 2? So your vectors you learned in class 11 and 12, all the vectors will apply here. Your physics vectors and all. And this is vector 3. So what can I say now? I can say x1 v1 plus x2 v2 equal to v3. So what am I trying to find? I am trying to find a, so I hope it's recording, right? Yes. So I am trying to find a linear combination of V1 and V2 such that resultant is V3, right? So how can I do that? See, so what is the first vector? 1, 1. How does that look? If this is my 1 and 1, so how does my vector look? 1, 1. It's a radius if it's a radius vector, how does it look? Like this. This is your vector. These are lines. This is your vector V1, 1, 1, right?
Yes, sir.
Similarly, your V2, 1, -1 will look something like this, right? So 1, -1. You're going 1 towards the positive x and then negative y. Same way. So my question is, can I take the linear combination of these two vectors and get what is my resultant vector that I want? I want this vector, right? This is the resultant that I want. 1, 0, right? So how will I get this? So using the trapezium or the parallelogram rule, right? So if I have this half of this vector and half of this vector, do you agree? If I do half times v1 plus half times v2, I will get the resultant vector, right? So you see, you put half at in x1 and half at x2, you're going to get this. I hope it is clear, right? So what are we effectively doing? So this can be compressed into a single equation. So this is what I want you to think about when you're doing questions. So when you have a vector and matrix product, what will you think of it like this? Like from this example, I'm writing, so I'm putting this matrix equation into this set of equation into a matrix. I can do this, right? So it is just, if you see your school days multiplication, this into this, into this, into this, plus this into this is equal to 1. Similarly, 1 into x1 minus 1 into x2 is equal to 0. Okay, so I want you to think of this as a linear combination of these two vectors or the column vectors, right? I want you to think of this way. Okay, so instead of multiplying the way you used to do, what do you want to do? You're taking linear combination of the columns. Linear combination of columns of A, right? So this is the introduction I want you to give, or the notation that you will be following throughout the next 4 sessions that we will be having. So if you have any doubt, you stop me now, ask. So these are the columns. So this is one vector, column vector. This is another column vector. So I'm taking the linear combination with these two values that is provided in the vector here over here. That tells me how much of the vector, first vector c1 I will take, second vector c2 I will take. Is that okay?
Yes, yes.
So others, do you from today we will not be do, huh? Yeah. Yeah. What is the question? You're muted, Monostrija.
I wasn't asking a question. I was just saying it's clear.
Okay. Okay. So for now, we have seen that this is how we'll be looking at. So what are we trying to answer in this class today? So we'll be trying to answer. So this is a solution that we already got. So there's a unique solution over here in this case. But it may not be the case. You may recall in your school days, you had all those determinant rules to say which is how many solutions, infinite solutions, one solution, so on. So we will be seeing how to understand that in terms of column spaces or linear combination of the columns. Okay. So before we go into that, let us do something lightweight. So these are the questions we will trying to answer. That how many solutions will we be having if n is if you have a tall matrix, if you have a fat matrix, or you have a square matrix, right? These are the three type of matrix you can have where m is greater than n is greater than m, and m equal to n, right? So we'll be doing all the subsequent theory will be based, 50% of the subsequent theory will be based to answer this question. And 50% of the subsequent theory will be based to answer what are known as eigenvalues and eigenvectors. So this is all is there in the linear algebra. Only you need to understand how many solutions you have. And for that, we're going to develop all the theory now. So first, we'll be giving you some, let us do some warm up. So you can, this you can try now itself. So you can help someone of you can help me. So trace, I think you know, is the sum of the diagonal. If you sum them up, you get the trace, right? So my first question is, trace is so what is it? So you have a circular symmetry, right? Or cyclic. By what do I mean by that? Trace of ABC is equal to trace of CAB equal to trace of. So I have brought this over here, so I can bring this over here, BCA. Okay. So we'll need to prove this for any two matrices. If I can prove for any two matrices, do you agree? It is true for any series of matrices, because these two I can club them up as single matrix, and this can be a second matrix. So by induction, it will be true, right? Yes or no? If I can show that for two matrices. Good. So can you tell me what will be the trace of AB? How will I write it? So A is a, I have written M cross N matrix. So let me just visualize this. Something like this. A1N, AM1, AMN into a B matrix, that is B11, B1N or M, because trace only has to be for a square matrix, right? Trace is defined only for square matrix. Do you agree? Because if you have a fat matrix, right, you will have a diagonal like this. So there is no question of trace, right? So only if the matrix is M equal to N, so you will have a trace. So that's why I am taking opposite shapes of A and B. Tell me. So what is the element AII? Can you tell me? So I want all the elements. I want this sum. Do you agree? Do you agree that I want sum of AB, II, I equal to 1 to M, right? This to multiply, you will be multiplying AB, you will get a, this is the M by M matrix, right? So M cross N, B, N cross M. So these are conformable. So it's a M by M matrix. Agreed? Okay. So what is AB into II? AB, the II means the diagonal elements. Say the first element of AB. What will it be?
A11 into B11.
Okay, A11 into B11. Then
And then plus
plus A12.
A1
So you
2
will,
plus B21.
okay. So AB11 will be A11 B11 plus A12 B A12 B21 and so on, right?
Yeah, till
Until and unless
A1
you
and
get and Bn1,
A.
right?
Yeah.
Yeah. So you will be having this as summation of I equal to 1 to m and summation of j equal to 1 to n, right? So let's see once again. So this, how many terms are there here? N terms, right? There are n terms. So n terms. So j equal to 1 to n. So ith element. So this is the ith element will be aij, as Ritik is telling me, into bji. Do you agree? This is very simple to check. Why do you know? See, these two are II, right? So if you want to write it in terms of a summation, you will be marginalizing over these two. Why? In you do you remember that A cross K, B K cross N? What is the product of AB? What is the shape of AB? It is M cross M, right? So you remove these two. So you want to remember. So whenever you are having a product of two matrices and you're trying to get the K, these you are all programmers, right? So product of two matrices should be very simple to you. So if you are trying to find Aij, what will it be? What element will it be? So in or just to familiarize you with the things that you already know. So Aij will be the product of the ijth element of this will be, say this is m cross n dimensional, this is n cross k dimensional. So how many, what will be the ijth element? Without drawing the matrix, can you tell me? So this will be the ith row of ith row and jth column. So now can you tell me? By multiplying the ith row with the jth column, you will get this. This will be
AI and
okay.
so AI while we go
A
down the entire
okay.
row, so that will vary from 1 to m.
You want to 1 to n or m?
N.
Right. So this is L. So 1 IL and this will be J. Right? Everybody follows? I hope everybody understood, right? So this is general formula. So now what can I do? What trick can I follow to show this? I can just change this I equal to 1 to n and I equal to 1 to m, right? And I can write B J I and A I J, right? I'm just reordering the terms, no problem, right? Same thing I've written. If you have any problem, tell me now. Otherwise, I'll proceed. So AB, or rather BA, J comma J, right? Yes or no? Trace of B. Okay. This step is clear, right? Okay. Since nobody is asking, so let's proceed. More terms and definitions before we get into the rigorous things. So angle between two vectors, what is that? So remember, we'll be following this notation. So you can think of transpose to X Hermitian. Hermitian is for complex vectors, right? Transpose is for real vectors. So if you have A plus IB and C plus ID, so what will be Hermitian of this? Can you tell me? So you recall your class 11 and 12. Hermitian means transpose complement, right? So the conjugate of it will be A minus IB and C minus ID. Why am I doing this? Why am I taking minus? Can you tell me? Why am I taking? So it's what steps do what happens in Hermitian is first you transpose. If I write Hermitian, just think that it is transpose a complex matrix, right? Transpose and then complex conjugate, right? So why am I writing this? Because can you tell me what is X transpose X for a real matrix? So X is say a vector x1, x2, dot 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 xn. So what is X transpose X?
Length of vector
The row
squared.
vectors.
The length of the vector. So this is equal to. So this is how we write a length of a vector or a Euclidean distance. We will go to norms in the last 8th session, which is the last on linear algebra, but we'll be using it throughout. So that I'm just defining it. So this is, do you agree? This is x1 square plus x2 square dot 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 xn square. Yes or no? I hope this is okay. So multiplying this into this into this. So it's 1 cross n into n cross 1. So it's a scalar, right? Always remember x transpose x is a scalar and it is the norm of Euclidean distance of the vector, right? Euclidean length of the vector. So whatever in school used to write for a vector, what do you remember? The magnitude of a vector used to write like this, right? From now onwards, for linear algebra, we'll be writing this as the norm with two brackets, two straight lines, because a single mod means for a complex number, right? So in complex school, complex numbers were also written this way, right? So you used to write a square plus b square, remember? So this is why I am writing x Hermitian x. So if I write x Hermitian x, do you see why I wrote x Hermitian x? For this vector, this one I'll get a square plus b square plus c square plus d square, right? Yes or no? I don't want negative signs, right? If this is x, x Hermitian x will be this. Always you will have the sum of the squares, yes or no? So I'm just telling why are we writing x Hermitian instead of x transpose. Transpose, if you used to write, if you would write, you would get negative signs, right? For transpose, if you would write transpose for complex numbers, yes or no?
Yes.
Is it okay or do I show it?
Because if we take the transpose, then iota and iota will multiply and it will become
Yes,
-1. So
-1. So that's why I'm introducing another minus, right? So that's why just remember this. So and try to practice also. X Hermitian is the complex analog of. So since we are doing abstract spaces, so we can do the same operation for complex spaces also. That's why I'm just defining this. So every transpose is same as X Hermitian X for real. So why am I doing it? Because for say if you are using signals, right, Fourier transforms and all, so which will be doing in 4th year, essentially you will be having this DFTs and so on, you will be having complex matrices, right? So in that case, you can't use X transpose X, you have to use X Hermitian X to find the energy of that vector, right? So X transpose, so transpose analog is Hermitian, right? So Aij bar is equal to, remember, just recall this, right? So I will write this way and this way so that you can remember. Good. I think you are getting it. That's why not telling me. I don't know. Okay. So do you remember now? Do you remember the relationship between a dot product and a? So do you see that this is sort of a dot product? For the time being, let's consider only transpose, right? Hermitian is just the same thing. If you're told complex, use Hermitian. So you remember, right? So x mod of x in your school days, you used to write mod x mod y cos theta as x transpose, not x transpose, sorry, x dot y, right? This is your dot product. This is how you define the dot product, yes or no? So theta was the angle between the vectors, okay? I hope there is no doubt. So what was x transpose y? So x transpose y was ax, ay. So if x is a I roof plus b j roof in your school notation, and this was a b ax, let us write a y I roof and b y j roof, it was ax ay plus bx by, right? Yes or no? Just because I and j had a 90-degree angle, we defined dot products this way. Yes or no? So this is definition. Remember that it's not any inherent property. It's the definition of a dot product, right? This is how we defined it to take components and so on. Right. So how can I write this if this was if I matrix matlab linear algebra vectors? So for physics and all, you took only 2-dimensional or 3-dimensional vectors, right? But you can have n-dimensional vectors, n numbers stacked to one another. So in that case, how can you take the product of two vectors? Dot product will be like this, right? And for us, all vectors are column vectors. So we'll be writing transpose into x. So for us, just I will be writing all vectors are column vectors until stated otherwise, right? Very good. Now, this, do you agree this is equal to same thing, xi, yi, I equal to 1 to n if it is a n-dimensional vector? Yes or no? It's the same thing, right? Here also you had ai, bi, right? Same thing you had. You just took the component and took the product of the first component with the first component of y, second component of x with the second component of y, and so on, right? That's how I am going to extend it to n dimensions. Are you fine with this? Then I'll proceed. Or please ask. Yes, okay. So this is how I am going to define a dot product, right? So now this will be the same as, so distance was written as this way in your school. Same way I'll be writing the length of these two vectors as the same. So distance was nothing but the length of the vector, right? This was your length. This is also your length. Do you agree? So we have seen x transpose x. We defined this is the length. X transpose x is equal to norm square or the Euclidean distance square. Clear? Very good. So you have, we define x Hermitian y as, or let's just define it for transpose for the time being. In case you are confused, you can write it otherwise, right? This is okay. So this is the theta will be the angle between any two n-dimensional vectors, right? We'll be using this extensively. So I'm just introducing everything that we'll be using as the tools. So inverses, you are very familiar, so I'll not go into it. So for a square matrix, inverse is the matrix that multiplies itself to get a identity matrix. Identity matrix being all ones in the diagonal and 0 at the column, other places. So now comes the first application of matrices. That is the Gauss-Jordan elimination method, or the Gaussian elimination method. I think some of you may have done this already in your numerical methods course. But anyways, let's do it. And I'll just show you why it is true. So for all this while, what have you done in your school days? You found the adjoint. So inverse, how did you find? Adjoint of A by determinant of A. Yes or no? For a matrix, okay. So if you think it is something is you're missing something to tell you, or you're missing something, please stop me, because I'm going to introduce a very important concept called elimination now. So this concept was introduced long back in the ages of civilizations like the Harappan civilization, and even before that in Egypt. So I don't think it should be a big problem for you all to understand. See, so if I do something like this, if I augment A with I, I'm trying to find the inverse, right? This is applicable for any problem, this elimination thing. And I do some operations. So see, if I have a row vector, which is x1, x2, x3, say, and I have a matrix, right? Matrix comprises of, say, A1, or let us write R1, R2, dot, 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 Rn. So can you tell me what is this X transpose? This is X transpose that I'm writing, because I told all vectors are column vectors. X transpose. So this is A. What does this mean? So we have seen AX is linear combination of columns, right? Yes or no?
Yes.
Yes, sir.
So we have seen that AX means whatever component we had for X, we took C1, C2, and we got x1 c1 plus x2 c2 and so on till xn cn, right? And similarly, what will this be then, if you have understood? Linear combination of
Sir, is it R1, X1, R2, X2?
exactly r1 x1 plus r2 x2. So linear combination of rows, right? Because you see, we'll multiply this with this element, this with this element, this with this element, and so on, right? Yes or no?
Yes.
So you will do it for every element in every row. So it's essentially saying you will do something like this: r1 plus x2 r2, so on, right? So if I do something like elimination, which converts so as that EA, right, is equal to identity matrix, right? Then what will be E times I? Can you tell me? If A is square,
E.
E, but what is E then? This is
A
a
inverse.
very good. So this will be
E
equal to
inverse.
E. Very good, very good. This is the interaction that I like. So this is E, which is equal to A inverse. Why is it A inverse? Just now we defined A times A inverse is equal to I, right? So E will be equal to A inverse. So do you see that if I take some row operations, I do some, so E is comprising of rows, right? Like this. If I have some row operation, that is elimination, and if I multiply this, it will be EA augmented with E, and this will become I, and this will become A inverse. Do you agree? Because this, it's n by n, this is n by n, this also is n by n, right? Right. So this entire matrix is n cross 2n, but you'll be doing the same operation across the columns, so you will be getting So these are called block operations. So E can be multiplied with this as well as this if they are same dimensional, right? You can check if that, if like in your, like how you used to do in school days. So you can just multiply this matrix inside this and inside this. But if it is not true, if they are, these shapes are not the same, they have to be the same shape, right? Or conformable, multipliable. So is this clear? So if I can arrange a schedule that converts A to I using row operations. So see the beauty here. If I can arrange, I'll be using this throughout, and you will also use this because this will be asked in every interview if you are planning to study, more. If I arrange this schedule such that I convert A to I will be automatically converted to A inverse if it exists. Otherwise, you will not get an I here in the beginning, right? So a schedule of row operations, right? Only row operations. I cannot do column operations. Do you see? If I do column operations, I'm gone. I have to do something like this side. So anything you do on the left is a row operation, or anything that you do on the right is a column operation, right? I showed you here. So left is a row operation and right will be a column operation. I hope this is clear. So now someone tell me what will be the steps that I'll be following. So I have this matrix A. I'll be trying and converting it to a inverse matrix. So first step, what will I do? So I'll do this question at the end. Yeah. And at the end of this course, I'll be sharing a feedback also, like don't feedback as in you just, all of you who wish to write something to me, write in directly in the form of the email. So I will not be this, because if you want me to change something, or do you like, if whatever you liked or disliked, please tell me. So that I can also learn to understand people and their aspirations. Okay. So your A matrix is this. So I'm trying to understand how do I get A inverse? Can you tell me?
First we write the augmented matrix
Good.
A I.
So this is A, and I will be augmenting this with an I matrix, right? As I told you. Very good. And then what will I do? So I have to arrange the schedule of someone else, not Ritik. Ritik, I think he already knows, he has already studied this in his numerical analysis. So others, a schedule of row operations or linear combination of rows. Any idea? Yeah.
We will
So,
multiply.
oh, yeah, tell me.
Multiplying the first row with 3 and subtracting the
Very
first
good.
row from the
Very
last
good.
row. I mean, we'll subtract the
Yeah.
last row with 2 into 2.
Very good. So this is your mechanical step that you'll be doing, and I will also be showing you. Everybody tells you how to do it mechanically, but I'll also be showing you what is the E matrix that you'll be having, and you will like it very much. See, so you are telling me R2 will be replaced by
3
R,
into R1.
yeah, R2
Yeah,
minus
R2
3.
minus 3 into R1.
Yes, right. So you'll get 2 comma 0 and 3 comma minus 1, right? So you're subtracting 6 from here into 3 is minus 9, right?
If I do 3 R1 minus R2, then the minus 1 will not be there. So will it be better?
What will I do?
If I do 3R1 minus R2, so it will be 0 comma 1. So the last row of the identity matrix, it comes itself.
No, but that you will be doing. I'll show you. But the steps are this. Always don't follow any other step other than this step. What is the step? First, this is called a pivot. First, you take this column, I column, I element. Then subtract everything that is below it and make it 0, right? Everything below pivot must be set to 0. And you will shift pivots this way, diagonally. This is the algorithm you'll follow, and you'll see why we are following this. Once you do one question example, you'll see exactly why I'm doing this. So now what will this second part of this be? 1 minus 3, right? And 0 1. Understood? Into 3, so it will be minus 3 0. Yes or no?
Yes.
Next, what will I do? Next is the what Jordan introduced. So once I have zeros here, now I can go the reverse order. So that's why I'm telling you will do that. So I'll be now going this way, because I don't have to worry about this operation anymore, because 0 into anything will be this will remain the same, right? Once I have converted a matrix into a upper triangular matrix, I can do it in the reverse order to get a diagonal matrix also, which is called a Jordan elimination. Okay, do you see why am I converting it into a upper triangular matrix first? So if I have zeros over here, so any operation I do with this element here, the other elements from the rows will not change, right? So these will all be 0.
R1 equal to R1 plus 3 into R2.
Yeah, that's what I'm saying. R1 equal to, I'm just trying to intuit why will you try first make everything in the lower triangle 0 and then trying to make everything on the upper triangle 0 and then get a diagonal matrix, right? Okay. So R1 will be R1 plus 3 into R2, right? So what will you get? You'll get 0 minus 1 0. And what will you get here? What will you get here?
Minus 8.
So you'll get
3.
into 3. So you'll get a minus 9. So you add minus 9 to this, you'll get minus 8 minus 3 0, or this is 3, right? So because you'll be adding 3 to this, right? Yes or no?
Yes.
Once you practice 1 or 2, this will become your best friend. Now what will I do to convert? I will do more row operations. Tell me what row operations will I do?
Division by 2.
Exactly, I will divide this by 2 throughout, and this I will divide this also. I will be multiplying by minus 1. So I can do row operations independently. I'll show you why. So what will you be left with? Minus 4, 3. This one will be 3 by 2 and minus 1, right? This will be your A inverse. Yes or no? So just check. So your adjoint matrix of this with your school logic is this diagonal remains same, minus 6 minus 3 by the determinant. Determinant is 16 minus determinant of A is equal to 16 minus 18 is equal to minus 2. So you'll get minus 1 minus 3. I made some mistake somewhere, surely. Minus 3 by 2 and minus 4, right? This is what it should be your. Okay. 2 and 8 will be interchanged, right? Correct only. -4 and 1. Right? 1, 1. So -1 here. These two will be positive. And that's what we have got, right? Did you understand what I did here? Adjoined by this. In case of an adjoint of a 2 by 2 matrix, if I select this, so I will have to stop this. So I'll get 8 goes over here and 2 comes over here. For the off diagonal, you just multiply by -1. I think you know this trick from 11 and 12, right? So adjoint A by determinant A used to find. So you're getting the same value, yes or no?
Yes.
So how do you know that this is a valid row operation? So can you tell me the matrix that I'm multiplying first case? So to do this, what is the matrix I multiply with this augmented matrix to get this operation? So remember, what am I doing? Am I changing the first row anyway? Here, first step, am I changing the first row? Am I not doing any change to the first row?
No.
If I'm not doing a change to the first row, what should be my row vector? If I am replacing R1 with R1, what should my row vector be? 1, 0.
Oh, 1, 0.
Right? Everything else will be 0. If you have many things, it will only be 0, right? Because it will be 0 times all the other rows. You are not doing anything to the other rows. Similarly, if I am doing it for the second row, what will I do? So I am keeping the second row same. So I will be keeping 1, right? Here. So R2 is being converted to R1 minus 3R1, right? So I will be doing a -3 over here, right? So this will be multiplying with the first row, right? And yes or no?
Yes.
Very good. So this is also called the A equal to LU factorization. Why? Because you see when I'm doing this, do you agree? When I'll multiply, just consider E and A. E and A, I will get a lower triangular matrix. What am I saying? Upper triangular matrix? Yes or no? Am I getting an upper triangular matrix here? These steps will make me get an upper triangular matrix with all the elements below the diagonal will be 0. Right?
Yes.
This step will give me upper triangular. I will give you these similar questions in the assignment. You will be able to see more nicely that how A equal to LU is very, very, very important. So do you see what is E inverse? 1, 0, -3, 1. Can you tell me what is E inverse? So again, adjoint. So the determinant will just be 1, right? Product of the diagonals for any triangular matrix. Because with 0, you multiply anything, it's going to be 0, right? So this will be, what is this? This term, what will I get?
3.
0.
So the inverse of this is, so if I multiply E inverse here, and if I do E inverse over here, so what will I get? I will get P, right? So these are swapped and the off diagonals are just multiplied with -1. Yes or no? What is the adjoint of this? You get from here, right? The adjoint, this adjoint matrix, this is adjoint of, say this is E. This is adjoint of E. So this element you will get by blocking these two, right? So this is the 1, 2th element. So this is -1 into 3, right? -3. So this is plus 3, right? So you get a lower triangular matrix or not? So E inverse is lower triangular, right? Whoever said it will be 0, did you understand? I'm just doing class 11 adjoint. Yeah. Yeah. So E inverse is lower triangular, right? So your any matrix can be written as a product of a lower triangular and an upper triangular matrix. It's a very useful result you'll be seeing in some questions that I'll be giving you, and also in some solving some questions that I have brought today. Let's solve some questions before we go on to. So this is known as the elimination method, which I'll be doing now. The same logic I'll be following before I go on to more abstract things. If you're getting the understanding of elimination, you've got most of linear algebra. So can you tell me how do I solve a large set of equations? So I have very big equation n cross n, and I have n cross 1, and this is equal to. How do I do this? So how do you think I do this efficiently? For 2, I do some manipulation and remove variables and do that. So I have given you the foundation to be able to do it. How do I do this?
We multiply by the inverse of A on both sides. So we will get.
So you are saying
X minus-
AX is equal to B. You will be multiplying A inverse on both sides.
Yes.
So you will get X is equal to A inverse. So this is your class 11 Kramer's rule. This is this though you can A inverse computation. Is it easy? Like how will you compute?
No, sir. It's very difficult for large matrices.
It's in a way it's ON. It's a very very large intractable problem, inverse calculation. Whereas you can do this as a ON cube question. So this will be a ON cube process. Unlike here, which will be our exponential process, because you'll be finding determinants and adjoints, right? Finding your determinant in naive algorithm is itself exponential. Do you agree or not? It's a recursive algorithm. So you can't do that. It's no software will ever do that. So your Chinese and Indians knew this 3000 years ago. They had solved questions using this. So it should not be very difficult. So what will I do? I've already given you the intuition. So if I have AX equal to B, right? So I'll do the same elimination on both sides. Okay, such that I'm left with a. So this will give me an upper triangular matrix, right? And this is some vector X, or say B tilde, whatever I've written here, right? So what is the benefit of doing this? So once you do this question, you'll understand, but do you understand from this big picture also? If you have all zeros over here and you have an X matrix, recall your combination of columns way of doing things. So B1 tilde all the way to Bn tilde. So what is can you instantly get one value if you have something like this? Which value can you get instantly? Yes, Brahmoji.
xn.
Very good. How? So your ANN into xn is equal to Bn, right? So your xn will give me Bn by ANN. Yes or no? I hope you understand, right? This is your EANN. You have done some elimination. Understood, others? Except Brahmojit and. So if you have understood, you good. So let us see how to. So this is the way you will be solving equations now. Whoever gives you any equation, if you have solved by hand, you will only do elimination. I think this will be also there in your programming assignments. So this will be, do you see you have a, when you do this elimination, you have ON square, and when you do reverse back propagation, So you'll have one more n, so it will be ON cube algorithm, right? So subtraction and finding out all this numbers. So you have to do this elimination for n plus n minus 1 plus n minus 2 and so on, right? So this will be your n into n plus 1. Yes or no? You have to do so many steps of just eliminating. So here you will do n minus 1 elimination, then you will do n minus 2 eliminations, right? So this is ordered ON square eliminations, right or no? N square eliminations into n comparisons. Right? Comparison, because with this you will have to also find the factor that you will be multiplying to eliminate. Did you understand? So from a 2 to the power n complexity, I've reduced to order of n cube complexity. Do you see the beauty of the algorithm? So there are many books that hate inverses, adjoints and determinants. So we will not be using adjoints and determinants for any spaces as such. We'll be only using them for eigenvalue. We'll see how to do that. So from now onwards, you will not be using determinants for anything. This is the entire law. The reason I'm showing all these steps. Okay, so if you have understood, let's do this. So 2, 4, 8, 3, 7, 14. So what will I do now? Let's say same way, augment this. So tell me the steps. What will be the steps? I think you don't need ON cube, you need only ON square complexity, because you can do factorizing instantly, I guess. There are lookup tables. In O1 complexity, you can do that. What should be my first step? What should be my first elimination row operation step? Tell me.
R2 equals to R2 minus 2R1.
So I will be subtracting into 2 from here, and I will be subtracting into minus 4. Yes or no?
Yes.
This is how I will be doing elimination. I will be doing for a pivot in one go. I will be making everything below it 0. Okay. I will not do for everyone like separately step by step. You also should not do that. So you'll make everything below it 0 in just one step. This is called a pivot again. So this will give me more understanding of pivots. So what will be the next matrix? Someone? Ritik already told me the operations. So what will be this element now? Tell me.
1.
So it's going to be 7 minus. So I'm just going to write it once. 7 minus 3 into 2, right? So I have multiplied and subtracted by 2. Understood? So this is 1. Someone else, the third one. So I just want you to understand elimination instantly and not revisit this when you are at home. That's why I'm asking. Good. So you are going to multiply by 4. So this term will be 14 minus 3 into 4. It's 2. Similarly, 4, if you don't understand, tell me, will be minus 2. And this will be, help me, 4, right? Check with me.
4.
Yes. So this will be minus 3. And this will be minus 24, right? I'm doing this. I'll do the same operation throughout the rows because I'm multiplying it with effectively with an elimination matrix that I have, right? Oh, and one more thing. How do I scale rows? What matrix will that be? Can anyone tell me? So if I have row 1 and row 2, how can I scale row 1 by a factor of a with what will be? So I want to convert this into R by a and R2. So if I have to convert this, what is I forgot to tell you. So what should be your elimination matrix? Should be
1 by a comma 0.
Very good. 1 by a comma 0, 0 comma 1. Very good. Just think of it as linear operations on the rows. Think of the row as a single class, instance of a class, instead of thinking of numbers as elements of the class. Okay. So now I will move to my second pivot. I told you this is my pivot 2. Right? Then what will I do?
R3 equal to 2 into R2.
Very good. So I will,
minus 2 into R2.
yeah. So I will multiply 2 and subtract. So I'll get 2, 0, 0, 3, 1, 0, 4, minus 2, and 8, right? Right? Then 7. Then this will be, third row will become, I'm not being able to calculate if someone, if you're paying attention,
18.
minus 18. So this to this, you're going to multiply by 2 into 2 and subtract from this. Okay, good. Minus 18. Good. So now how will I get x3?
R3 equal
minus
to
18 divided by 8.
So x3 is going to be minus 18 by minus. So x3 will be minus 9 by 4. Agreed? Yes or no? I hope this is clear. Next, what will I do is, now can you tell me, I will just show one more step and then we'll go to the next part. And then you can, your assignments you can try.
Now we put the value of x3 in the second row.
So now here you see, as he's pointing out, so it's, this row will be x2 minus 2 minus 2x3 is equal to minus 3. Yes or no? This row is this. So now I'll be putting minus 9 by 4 over here. So what will I get? X2 equal to minus 3 minus of 9 by 2. Yes or no? So I'll get minus 15 by 2. Agreed? Very good. Good. It's matching from my computer answers. Good. So now we'll be going into, similarly, you have two values. Others, what will I do? 2x1 plus 3x2 plus 4x3 equal to 7. I know x3 as minus 9 by 4. I already know this by minus 15 by 2. And similar with using this, I'll get x1. You please check the calculation. I have done it. I'll just write it down. X1 is equal to 77 by 4. Okay, because this is my own made matrix, the answers are not so beautiful. I just made elimination simpler. So did you understand? So if you have hundreds of, so you can write a code to do this, right? Right. You can also do something like, what can you tell me? After you have got this, you can also do a Jordan elimination. Make everything above it 0, right? If you do that, then what will happen? You will only have a diagonal, right? So you'll have 2x1 tilde equal to, say, this will become some b tilde equal to b tilde. This will become some c tilde, and this will become some d tilde. So you will have some, so diagonal, so 2 will remain the same. This will also remain the same. So x2 will be equal to some c tilde and x3 will be equal to some d tilde, which will nothing but be minus 9 by 4, right? You'll be left with that. Do you see what I'm saying? You can also do an inverse elimination to remove everything above it, right? Just now, first you go from top to bottom, and then you go from bottom to up. If you want to do it, otherwise you can just put the values and see, right? Understood, or is it not clear? The inverse elimination is clear, right? Good. So let's do now what is called, now we'll go to, this is all like the foundations to understand what is the abstract thing called a vector space. So a vector space is an object on some objects like reals and complex numbers. So if you have done abstract maths, it's a field, right? The field has two operations, addition and multiplication. What is a field? Does anyone know? So I will not do what is a field. I will just give you a very vague idea of what is a field. A field is for each of this operation, you will have an inverse. So you have an additive inverse over here, where x plus minus x is 0. And you will also have a multiplicative inverse such that x into minus x is equal to 1. Similarly, you will have other properties like x plus y plus z is equal to x plus y plus z, which is also called the associative property, and so on. All normal mathematics algebra rules must hold. Rules hold, loosely speaking, right? So, but whenever you're told about a field, you just think of real numbers, complex numbers. So real numbers and complex numbers, for x, there is a minus x, right? And for say another x, there is also 1 by x. Agreed or not? Similarly, you have x plus y is also equal to y plus x, right? For these two, y plus x is equal to x plus y. Similarly, xy is equal to yx, and so on. So it is defined on these fields. So you see a vector space V is a subspace over is a subset of f to the power n, not subspace. I'll not go to subspace now. F to the power n. What does it mean? For now, for all this while, what did we define vectors as? Rn, right? So this was x1 was a real number, x2 was a real number, xn was a real number. Yes or no? This is a real, this is a real, and this is a real. Agreed? So it's a Cartesian product of n real numbers. Right? Good. You know, right? Rn you must know. So you will have Fn. So Fn can be either Cn, n complex numbers, or n real numbers. So a vector comprises of n real numbers or n complex numbers. For our case, that will be considering throughout, right? Everybody happy?
Can you
So
repeat the last few seconds?
a vector consists. So you know what is a Cartesian product, right? So R square is x comma y such that
R cross R.
x belongs to R and y
R,
belongs to R.
to R.
So here you will have n numbers, x1 through xn. All of them will become to belong to R, or all of them will become to C, belong to C. Agreed?
Yes.
So a vector can be a list of n real numbers or n complex numbers. Understood? We are only going to do n is finite. Agreed?
Yes.
So now are you seeing the abstractness? For the time being, we were all thinking of vectors as lines, but now we have converted them into lists of numbers, for which all these properties which I'll be telling you will hold, right? This is the little bit of an abstractness you need to understand. So x plus y must be belonging to the vector space. So this is called a closure. We'll do an example, it will become clear. Then it does not matter if you add y plus z first or x plus y first. This is called associative. Similarly, commutativity should also be there.
Groups.
Exactly, you'll have the properties of groups because it's an addition properties, right? It's an abelian group, right? So it's more on a group. It's defined on a field, right? A vector space is defined on a field. So these are properties of a group, all right, but it's also a vector space. So it has more properties because each of these x contains elements from a field, right? What's it? X is made up of belongs to f to the power n. So it's much more than just properties of group. So it is holding for the entire collection of the list, right? So it will have two properties known as additive properties and scalar multiplication properties. So this is what you have done in school all the while. You have added vectors like this, like normal numbers, and you have multiplied some real value c1 with a vector, right? This is what we have been doing, where you multiply each of the elements with C1, right?
Yes.
So this is what, these are the two rules. So you can add in any order, you can do commutativity, you can also get a additive identity, which is a zero vector, right? And you will have an inverse. We'll do a very interesting question, you'll understand. So alpha for a scalar, so let's say alpha and beta belongs to the field. So alpha into x will belong to the vector space. So C into x is a vector, right?
Yes.
Similarly, multiplication of two elements from the field will also belong to the vector space, and you can do associativity like this. Similarly, you can do distributive property, that you have all these properties for normal groups. There are two distributive property where you have two scalars and where you have two vectors. All these things are normal algebra. Do you have anything that I need to explain? So it's just algebra, opening brackets, closing brackets, and taking associating things. So there's nothing to explain, right? So I'll just do an example, it will be clear. Right? Each property is known to you. You have known this property since your childhood days for any numbers, right? So let's see. This is the question I want to solve to get you the understanding of what is a vector space. So a set of random variables is a vector space over real scalar field. So my field is equal to r to the power 1, right? I have told you a random variable, right? I'm trying to link your random variables with today's discussion. Yes or no? Your field is r. So random variable takes anything on the real number line or not?
Yes.
So first is the additive property. So if you are, I think if you have to see the additive property. So what is the first property that it must have? X belongs to the, say the vector space is V of the random variables, and Y also belongs to the random variable. So X and Y are RVS. So do you agree X plus Y is also a random variable?
Yes.
So if it is a random variable, it will belong to that vector space or not? So this is the vector space. X and Y belong vector space of random variables. Agreed? So X plus Y will also belong to the vector space. Similarly, very short I will do. X plus Y plus Z is equal to X plus. So I can add two random variables this way or this way. Does order of adding random variables matter? Order of adding random variables don't matter, right? This is your associative property. Similarly, number 3, what should be number 3? Do you agree X plus Y is equal to Y plus X in case of random variables? Addition of random variables? Yes or no? Okay.
Yes, sir.
Now what should be the fourth step I should do? If you have understood. So is 0 a random variable? Also?
Yes.
Correct. So anything that you're mapping to 0 is a random variable as well. So 0 also belongs to the random variable space. So x plus 0 is equal to x. We agree? Simple variable or holds. Number 5, if x is a random variable, minus x is also a random variable. Right? So x plus minus x by definition is 0. Agreed? So we have seen all the additive properties. Similarly, for random variables, we can see multiplicative properties for scalars. So say alpha belongs to real number. So is alpha x still a random variable? Right? So 10 times a random variable is also a random variable, right?
Yes.
So it's closed under scalar multiplication. Similarly, alpha beta into x is same as beta into x. So I'll give you an example. So this is 10x, say 2. So 10x into 2 is same as 20x. Yes or no? For a random variable. So you have associative property here. Number 3. What is the third property? If you recall, distributive, right? So alpha plus beta into x, what will it be? Alpha x plus beta x, yes or no? Random variable follows all these things for a normal algebra space. So sum of two random variables into alpha will be alpha x plus alpha y, yes or no? 1 into x is also x. 1 belongs to real. Okay? Any step you did not understand, I can give you a question where I can give you polynomials and you have to show this. So do you agree polynomials will also be a vector space, a set of n or n degree polynomials? That is a potential homework. A set of degree n polynomials is a vector space. Degree n polynomials with real coefficients. Okay? Are you getting the vague idea why it will be a vector space? This will come up in your assignment maybe. If you have not understood, tell me. Is it clear for the random variable? And okay, it's clear, I guess. So
What does these are just properties that you told us.
Correct.
But what does it actually mean for?
I'll show you. What does it mean? Just now I'll show you. Why is it important? So you have to understand what is a subspace to appreciate that. So any vector space is also a subspace on Fn, right?
Yes.
So I'll show you what does it mean. So a subspace, by definition, is a subspace of a vector space such that any linear combination belongs to the set, right? Why is the property important? So as you're telling Ritik, without axioms, once you appreciate it, you will understand. So mathematics, I think that you know this if you see a lot of YouTube videos, there is the undecidability in mathematics. If you do not have enough axioms, you cannot prove enough theorems. So just a side note. Axioms are known to be ground truth to prove anything. They are assumed. Okay. So anyways, so ax plus alpha x plus beta y should be belonging to the subspace. So if you have a subspace, any linear combination of elements in the subspace must be closed. This is why I defined all the properties above. So do you see? So I'll give you this example. So see this one. So x comma y such that x comma y greater than 0. So you agree this is the space? Yes or no? So is this a subspace? Why have I defined this? You'll understand now. Is this a subspace, Ritik?
Yes.
So you choose any two vectors, you give me any two vectors in the subspace, I will show it is not a subspace. Unless we interact, we will not understand.
1 and 2, 1 comma 2 and 2, 1.
Okay. This is, you're saying 1, 2 and 2, 1, right? Happy with
Yes.
my two vectors? So now if I multiply, so this is the subspace. So this
Oh, if you
subspace,
multiply with a negative number, it will not be.
very good. So S is a subspace of R square, right? Right. So
Yes.
so what did I tell you? So now do you see the usability of multiplying with a scalar? So S is a subset of V is a subset of R square, and S is even a subset of V. There are two levels of subsets. Right. So what is the set of scalars here? Can you tell me? So the properties that are defined. So your vector space is defined on the R square. So the field is R equal to, right? The field
Yes.
on which, right. So I can select any real numbers, yes or no?
Yes.
So, and these will still hold. So you see, for these properties will not hold if you do not have all these constraints. Just to have, so I'll multiply by a negative, very large negative number. To everyone see the sum of these two vectors, the resultant vector will be somewhere here, which is outside the subspace. So once you get this feel good factor, you will be like, linear algebra is very beautiful. So you'll be so nice when you see whatever you do, you have to do on linear spaces. You have to take linear combinations only. So once you take linear combinations, that should be inside the subspace. Similarly, x, y greater than 0, is it a subspace? Someone else? People who are not interacting. See, if you don't interact, you will not feel the interest like others are not feeling in such interesting sessions. You will also not feel. So do you agree this is x, y greater than 0?
It is a subspace.
Okay, again. So I will select one vector like this and another vector this way. And I select this. For both these cases, x and y multiplication is greater than or equal to 0. Yes or no? But any linear combination of these vectors, what is it? Will be somewhere here, right? Which is not belonging to S, right? So not a subspace.
Can you repeat it again?
So any linear combination must be in the subspace. That's the definition of a subspace. So any two vectors you choose, any number of vectors you choose from a subspace, that should be closed under a linear combination operation. Now, is it okay?
If it were x comma y greater than 0 only and not greater than equal to,
Then also, na, this and this still be this. The resultant vector.
acha, yes, yes.
Understood?
So the other when we define a vector space, we are essentially saying that all those properties that are listed will be valid for all
Exactly.
the members
Very
of
good.
the.
Exactly. So you will be able to do basically what you have now understood. You are getting the feel good factor is. So once you have a vector space, you will be able to do linear operations on that space. Now do you understand? And you can scale those vectors and add those vectors, and you'll still remain on that space.
Yes, yes, understood.
So that's why they're defined this way. So y is equal to mx plus c. Is it a vector space again? So it's a line.
Yes.
Again, you're saying yes. So all the vectors must be present on this vector, right?
Yeah.
Right.
But
So if I scale this up this way, and if I scale this vector this way, if I just scale it, it is not present on this line. Do you
okay,
agree?
okay. Yeah.
Even
Yeah.
just alpha into x is not belonging to this vector space. Others, did you understand?
No.
That's why I knew you did not understand. So all these are the elements of this vector space, yes or no? So what is the radius? What is the vector for each of these elements? This, right?
Yes,
This is
yes,
this
yes.
is this is the this is your vector, which I'm appeared on the
Yes,
screen.
from the origin to that point.
Yes. So if I multiply by some number alpha into x, so it will be
Then the
outside.
resulting
It will
vector
not.
will be outside the line.
Yes. So it's no more in the
It means
space.
any line is any line is not a vector space, right?
No.
Any line within
There
a vector space.
only one thing will be a vector space.
The real vector
If
space itself.
this is a vector space. Further, it is not. This is a vector space. I'm telling you before only. Now you think why it is a
Oh,
vector space.
because every
Any
vector
line,
is lies within the vector space.
Exactly.
any
It,
line passing through the origin will be vector subspace.
yes, will be a subspace. Because see, you take this vector along this line, you scale it up, it still stays on the line. You take a negative, still on the line. You take a resultant vector, it's just v2 minus v1, and you will just have a magnitude along this.
Yes.
So any vector space must contain 0. So I could have shown this another easy way. So x plus minus x is equal to 0, which is not in the vector space. So if 0 is not in the vector space, it's not a vector space only. Understood? So 0 must be there. Okay.
Yes.
So before I go into a more complicated question, can you define a few vector spaces on R3? Some vector spaces on R3.
Any line passing through origin, any plane passing through origin.
Very good. So one will be line through origin. This is your one-dimensional vector space. So your n-dimensional vector space can contain any lower dimensional subspace. This is what I want to say.
That is, sir, every subspace of a vector space must pass to the identity element of the origin of the vector space.
Every subspace must have the origin. That's the idea. Because you must have x plus minus x equal to 0, right?
Mm.
Which is also has to be belonging to the vector space.
Hmm.
So because this is a combination, if x is belonging to the vector space, minus x must also be belonging to the vector space, right? So if you add them by the properties we have defined in the additive properties, this is nothing but 0. This is why you need axioms. If you did not have axioms, what would have happened, Ritik? Any person could have come up and said this is a whole, x plus minus x is a. It is not equal to 0, even if it is obvious to you. So I just wanted to see, I never got this understanding of axioms and importance of these unless I went very late into my 4th year, and then I came to my PhD. I understood. Right? These are very important things in mathematics. So this is why you need axioms, that this sum of these two, you need concreteness, has to be equal to 0, so that nobody can argue against it. So you said a plane through origin and entire R3. Can you tell me one more vector space? This is 3-dimensional, this is 2-dimensional, and this is 1-dimensional.
Origin itself.
Exactly.
Dimension.
0 is a 0-dimensional vector space. So if everybody has understood, so any vector space Rn can contain Rn minus 1, Rn minus 2, and so on till 0-dimensional spaces, right?
Bah.
Yes. So this is why am I doing this? Because I will bring this up in matrices, column spaces, and other spaces. So it will become, in the next 1 hour, you will have matured a lot. Why, you'll see. Let's now use this concept of vector space to understand what is a span. So span. So in school, I think you had studied in 11 and 12 that given two independent vectors, you can always can span the entire R square, right? Entire plane. What do I mean by that? Any resultant vector can be written as a linear combination of these two.
Yes.
So I need two independent. So there's a trivial example. Can you tell me what is the trivial example that you're using always, but you don't know? Like from birth, people use it. Like not birth, maybe class 4 and 5.
Can you repeat the question, sir?
So there is a trivial example where you use the span example even from class 3, 4, 5, 5 onwards. When you start to read graphs, what are the two
R cos
vectors that
theta
you?
and R sin theta.
No, you take
I cap
one
and J cap, matlab X and
exactly
Y.
I cap and J cap, which is 0,1 and 1,0.
Isn't that what I said? R cos theta, R sin theta.
Oh, you're saying R. Okay, in that some way. Okay. Yeah, true. I'm not even considering. So any vector R can be written as R cos theta I roof plus R sin theta J roof, right? So similarly, if you do not have even perpendicular orthogonal vectors, you can still change them, right? Scale them to make a parallelogram. This is the intuition I want you to have. So you can always scale them accordingly to get it, right? So this you will get one like this, and from this you will get this. So if you have n independent vectors, how many dimensions can it span?
N dimensions.
Dimensions is max is Rn. I have said because n independent vectors, but given any n vectors, how many non-zero vectors, how many dimensions can it span? Any n vectors?
At most n dimension.
At most 10.
Okay, and at mean
0.
no
For 0 vector.
0.
One
Okay,
and
I'm not non-zero.
For 1. 1.
1. So how? Why? So all the vectors are like this, right? So this is the type of, and this should immediately click in your mind that are they independent? Are they dependent? These questions you should ask always, and then you will be able to understand what is the dimension of the space that they're spanning. So this is the intuition of a span. So let us do mathematics for the span. So what is a span? A span by a set, as Ritik was telling me, will be mathematically written as all vectors which are the linear combination of the vectors that is spanning the set, right? So this is a fancy way to say alpha I belongs to R or alpha I belongs to C, right? Do you understand? This image I have written in form of an equation, a set. It's a set of all those vectors that are linear combination of the spanning vectors. Yes or no? Not understood?
All the vectors that lie within what, sir?
So these are your spanning vectors, right? Say I roof, J roof, K roof, right? So I want to take combinations of all these vectors in all possible real number lines, and then I will get the span of that vectors or this vector space.
So that entire vector space will come.
Exactly, that entire vector space will be coming. This is the mathematical way of writing it. Do you see the set theory definition of writing it?
Intersection of alpha I and theta I.
So here, for example, I'll show that S is a subspace of V. So can you tell me how to show that? S is a subspace. What should
Linear
I?
combination of every
Exactly.
element of S remains in
So
vector space.
X plus. So let us say X belongs to span of S, and Y also belongs to span of S, right? These two are the vectors that belong to the span of S. Agreed? Now if x plus alpha y belongs to span of S, for all alpha, it is a vector space, right? So you can also multiply beta with this if you want, right? Now tell me, what should I? Both are right. Even if you do not multiply beta, you can scale y accordingly, no problem. So beta into x plus alpha into y. Let's write the other way. It will be conventionally easy. So now what will I do to go further? Any idea what I should do? So x can be written as, since x is in the span of S, so x can be written as some, tell me if you understood, some alpha I vi's or not,
Mm-hmm.
right? That's how I have defined x is in the
Yes.
span of S. And similarly, beta y can be written as some beta I vi's. Agreed?
Hmm. And beta into by will be some constant, and alpha into alpha I will be some other constant, and then there's some.
It's a similar. So x is is in the set. So there is a set of alpha i's, right? Such that you can take the linear combination of the vi's. So for example, 1 comma 1. So 1 comma 1 is 1 into I roof plus 2 in 1 into j roof, right? So the alphas are 1 comma 1. So there exists some alphas to take the combination to get your x, right? So since x is in the span, so you can take some. Now you can do simple algebra with it, right? So instead of writing alpha is, let's write ai and bi's for obvious reasons, right? So now what will it be? This step, I equal to 1 to n ai into alpha plus bi into beta into vi, right? So I have, my screen has stopped for some reason, I don't know why. Am I audible? I don't know what happened. Screen has frozen. Now it will come. Okay, so this is true, yes or no?
Yes.
So this also belongs to some gamma I, which is also part of the field by definition of field. So 2 into 2 plus 3 into 3 is, say, 13, which is also a real number, right? So for all being real number, so these are all real numbers. The product of real numbers, and some of them are also real number, yes or no?
Yes.
Hmm.
So alpha I 1 to n is delta I vi. So does this belong to the span of S?
Hmm.
Good. So a basis is called the minimal spanning set. What does it mean? So for example, why am I telling you this? So since, think of this 1 comma 0, 0 comma 1 and 1 comma 1. Can you tell me a basis? Span of this is r squared. Do you agree?
Sir, can you
Yes.
repeat what you said?
Yeah, so my screen again has frozen, so I have to wait. So I have 3 vectors. I have 3 vectors, 1 comma 0, 0 comma 1 and 1 comma 1, right? I want to ask you, what is the span of these 3 vectors? What? Yeah, go ahead. This is your 1 comma 0, This is your 0, comma.
1, 1.
I'm telling the span. What is the span definition I told you just now? It's the set
Minimal.
of
No.
no
Span is the set of all the vectors whose linear combination will give the entire vector space.
no span is the linear combination of the elements given to me. That's what I'm saying. What is the span of these three vectors?
R square. The 2D plane.
Yeah. Span means you have to take linear combination of the vectors given to you.
Hmm.
And it will give you a set of vectors, right?
Hmm.
And what vectors will you get from 1, 0, 0, 1, and 1, 1?
We enter 2D plane from 1, 1.
Okay, and now you tell me what is the minimal set you can construct to map the entire 2D space from using these two vectors, using these three vectors. Do you need three vectors to map the entire 2D space?
No, only two vectors.
So any two independent vector will do it for you? This one,
Yes.
this one. Exactly. So these two or these two will any of these will help me. First two or the second two will help me do this. So next would be sum of subspaces. This is also a very simple thing. This you can only tell me. So if you have understood, just wait. I'll just go back and rejoin. Okay. So let's do it for the sum of two vector spaces. So x and y being two subspaces of the vector space V, and we are summing them up. So what does the sum of two vector space mean? So one vector I will take from the first vector space, and the second vector I'll be taking from the second vector space, right? And I'll get a set of vectors, right? Yes or no? So I'll give you an example, rough example. So one vector space say is R square, right? Okay, it is a vector space.
Hmm.
And another vector space is a orthogonal line in the third dimension, say Z. So do you agree that if I take any vector in R square and add with any component on Z, I can map to entire R3, right? I have three. So I will be taking a vector from R square, one vector from R square, and one vector from the third dimension. This is Y. Say Y, this is X.
Hmm.
And Y is say some R. R and R square both are subspaces of R cube. Yes or no?
Yes.
So R comma and if I sum one vector from here and one vector from here, I will be getting some other span, some other subspace. Yes or no?
Hmm.
Okay. So now I have to show if I have such say two planes, two planes and so on. So in that case, passing through the origin may not be a vector space, but let's think of the two vector spaces. You can sum them to get the span. So this is now the question of spans, right? So you are going to span the entire set. Once you have two vector space, two planes, you will be taking the higher space, say R3, three R3 planes in a four-dimensional space. So you'll be entirely covering the four-dimensional space roughly. For visualization purposes, please refer to this. Okay, so now we have to prove that the sum of these two elements is a vector space. How can I do that? clear, right? First vector I'm taking from, so x plus y is x plus vector x. X is belonging to the first set and y is belonging to the second set, second vector set. And this is my sum of two vector spaces, right? So I have to show that this is a subspace. So what I have to show?
Alpha x plus beta y belongs
to this set. So for an element, say z1 belonging to x plus y. So z1 should be, you can write z1 as sum x1 plus y1. Yes or no?
Yes.
Is everyone on the same footing? So if z1 is in the x plus y space, I should write capital X plus y subspace. There should be two vectors to x and y1 belongs to y, right? I should be able to write z1 this way from the very definition of this set. Similarly, if I have z2, I can write x2 plus y2 for some x2 belongs to x and y2 belongs to y. Yes or no?
Yes.
So as Ritik is telling me, just take the linear combination and see. So whenever subspace question is coming, just take linear combination of the elements in that set. You are done. There's nothing to think also. So you'll get alpha into x1 plus alpha into y1 plus beta into x2 plus beta into y2. Right? So what will you get? You'll get alpha plus beta, or rather alpha x1 plus beta x2 plus alpha y1 plus beta y2. Now what does this belong to? And what does this belong to? Tell me. So x, yeah,
x and y.
x and y. This is the linear combination of two vectors in x,
Oh,
and
yes.
and this is the linear combination of vectors in y.
Right.
So you will have recursive definitions being used everywhere. So your z1 alpha z1 plus beta z2 belongs to your x plus y. Okay. Similarly, now we come to a bit related to matrices. This was warm up. So this is your relation to matrix. So let Sx and Sy be two spanning vector sets. So what does spanning vector set mean? I have defined just now. That span x comma y. What does that mean? Someone?
They cover the entire x and entire
Exactly.
y.
So Sx is sum x1, x2 dot 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 xk such that span of Sx is equal to x, right? That is linear combination of alpha I xi's, right? Roughly speaking, set of all alpha is xi's. Good. Then Sy will be y1, y2 dot 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 yk, right? Thus that span of Sy will be equal to y. Now I am telling you, show that union of these two sets would span x plus y. Isn't it trivial? Just from here, why is it trivial? Just tell me. So what is Sx union Sy?
Span of x, entire x union entire y.
No, Sx is a set of vectors, right? It is a spanning vector space. Spanning vectors. These are spanning vectors. There is a difference
X1,
between spanning
comma,
vectors.
y1.
Yeah, correct. So, Hussein, there's a difference between span of a vector space induced by how to say it simply. See, you have say n vectors These n vectors will span a vector space, but these are itself some n vectors, right? They are independent or non-independent, some vectors in Rn or Fn, right?
Span is the entire region where it is.
Exactly. They will span the entire region using these vectors.
Achha.
And this is called the set of the spanning set, right? Spanning set spans the vector space, right?
Achha.
Spanning set is a set of vectors, and the minimal set is called the
Basis.
correct. So that's what you use always in your exams and questions everywhere. If you give gate and all, you'll be asked just to find basis vectors. Anyways, so basis must be independent and they must span the set, right? These are the two conditions of basis, right? Basis must be independent and must span the space. Then only you'll get a basis. Then only it's minimal. So okay, Sx union Sy is the spanning set xk, y1 union y2, yk, right or no? So tell me, so what will be the span? So if you say Z belongs to the span of Sx union Sy, right? I've already done this question here. So you must be able to tell me. So how can I write Z as? I will not write unless you tell me. Because this is very easy. Z, if it belongs to this,
alpha 1 x1, alpha 2 x2 till alpha k xn, and plus beta summation of beta I yi, and then we will show that these individually belongs to x and belongs to y.
Very good. So only Ritik has totally understood this. Now he will understand linear algebra like very easy. Others also must similar. Others, are you okay or do you not understand? Please, I don't want to teach a single person. So this will belong to x and this will belong to y. And typically you should show in both directions. So if you are showing in both directions, this is equivalent, right? In both directions. So if you start off here, you can go back here. Similarly, if you start from here, you can come here. There is no unidirectionality here. We'll be seeing where you need to show both directions, but here it is not required, right? So if you can write x plus y, you can start from here and go upwards. Same steps backwards, and you will get Sx plus Sx union xy. Others you understood, right? So if Z is belonging to this set, Z can be written as this belongs to x, this belongs to y. So Z belongs to x plus y. So Sx union Sy spans x plus y. Now, the third or the most interesting part of it is called a direct sum, which I have shown over here. This is a direct sum where your dimensions will increase directly. That is like this. So what is a dimension of a space? First definition is now we'll come to dimension of a space. So dimension of a space is, do you have the intuition from now? What should it be? I have given you enough examples to yourself define a dimension of a space.
Number of elements of basis.
Yes. See, here you have 2 elements in the basis to span R2. 3 elements in the basis will span R3. Similarly, 4 elements basis will span R4 if they're independent. Of course, basis is independent. So number of elements in the basis. So I am saying that Sx intersection Sy only contains 0. So any two intersection of any two vector spaces, do you agree they will always contain one vector at least? That is the 0 vector. Yes, that is that. If you have understood a lot of it. Okay, so if you understood that, so if it only contains the 0 vectors, what does it mean? So Sx intersection Sy, right? Right? Is phi. Yes or no? Because you only contain 0 vector.
Always
So the
only
spanning.
5. Oh,
See,
yeah,
I'll
basis is
show you.
independent.
Basis is independent. plus your
they also contain, they will
only 0 they are containing, right? So you're given x intersection y is equal to 0, right? Only the 0 vector. So when will it be? So I am telling you, you have to show that x plus y, which is equal to, do you agree, sx union sy, span of, right?
yes.
So if that is the thing, so I am telling you, so this should contain, this should be a basis. Sx union sy should be a basis. That's what I'm saying. If it is the basis I can show, then I'm done, right? So x plus y is spanned by sx union sy. Okay, so the what is the dimension of x? So this set, right? So sx union sy, how many elements will it contain? So if they're independent, do you agree there is no solutions to alpha I xi plus beta I yi equal to 0? Do you agree? Not
Yes.
equal to 0 because they are independent. I have told you, since sx and sy do not contain any element, their intersection is 0. So this has no elements in common. So sx union sy will be the basis. Do you agree?
Yes.
Sx intersection sy will be basis. And how many dimensional will it be? Basis for x plus y. So it will be k plus l dimensional, right? And what is the dimension of x and what is the dimension of y? K, and dimension of y is also l, right?
Yes.
So LHS, RHS is matching or not? So what is the trick over here? You have to just show that since they are independent by definition, there cannot be any combination of alpha i's and beta i's such that this is equal to 0 except for alpha I equal to beta I equal to 0 for all I, right? This is the only combination that you can have. So that will show that Sx intersection Sy is an independent set. Thus, it is a basis, right? So to show it's the basis, you must show that it is independent. So we have all. So what are the two things you need to show if it's to show a basis? For basis, what do you need to show? One, they are independent, right? Or this should be step 2. What should be step 1? Basis of a space spans S. Everyone with me before? So this is if you have understood this, now linear algebra is just using these fundamentals. So it's just x plus y. Linear algebra is. You just see now. I'll show you. So a matrix. Let us come back to a linear algebra now. From those very abstract spaces, let us come to matrix spaces now. Okay. So our matrix space now says a m cross n dimensional matrix. So I can say they are n m dimensional vectors. Yes or no?
Yes.
Very good. So we define the column space of the matrix as the span of all the column vectors. Happy? There's nothing difficult now. We have understood span, we have understood basis. Similarly, so the dimension of the column space is known as the rank. Why is it important? We'll see in just a while. Dimension of column space. Right? Is known as the rank. Next, column space of A transpose similarly will be the space occupied by, I will not say, tell me. Column space of A transpose, what will it be? If this is your A, now let us write, if A is R1, R2, R3, Rm, right? What should be column space of A transpose? What is A transpose then? R1, R2, Rm, right? Yes or no?
Yes.
So what will be the column space of A transpose? The span of R1, R2, Rm, right?
Yes.
Now, these two you have understood. There are other two spaces known as the null space and a null space of A transpose. So what is a null space? A null space will be a space for this solution. Why it is important, I'll show you. So if there is an x such that Ax is equal to 0, so x is said to belong to the null space of A. Right? Okay. Similarly, if x transpose x is equal to 0, x belongs to the null space of A transpose. These are the definitions. For the time being, you just do with the definitions, and then I'm coming to the why is it that is important. Okay, so you tell me at max for a m by n dimensional vector, a column vector, say 1, a2, a n, right? M cross m dimensional matrix. What should be your maximum column rank or your maximum rank of this matrix or maximum column space dimension?
Number of rows.
Number of rows, sure. So I'm saying column space is the span of A1, A2, AN, right? This is your column space of A. I defined it. Right? So what can it be at max? If I'm not given anything about A and B, it can be equal to n, right? It can be equal to this only, like dimension of the column space I'm meaning, dimension of this. So it's a number of basis vectors, right? Yes or no?
Yes.
But what is the number of basis vectors here?
N.
Exactly, at most it can have n basis vectors, yes or no? At most n basis vectors. At mean one basis vector. Similarly, you can go about doing this. Now we will be seeing how this column space and the null space are related. So these are related in some way. Do you see the column space is a subspace? So column space of A is a subspace of how many dimensional space? You will get it from. Very good. It's a M subspace of a M dimensional space, right? And what is the null space of A at subspace of? From this definition, you can tell me. So Ax is equal to 0. So what should be the dimension of x? What should be the?
0.
No. I'm saying there's a solution other than 0 that maps this. So if this is m cross n, this should be n cross 1. So null space is the subspace of r to the power n, which is the number of columns, right? Because why am I not writing it this way? Just to intuit the thing. So this is, you will have essentially this, right? This is your Ax, yes or no? Right? Ax is something like this, right? You have n columns. For each column, you will have a scalar. So you will have this as summation of alpha i's x i's, right? As I told you. Very good. So I am saying So your null space has to belong to these. This vector is the element of the null space. So which is n-dimensional. So it has to be subset of the n-dimensional null space. We'll be seeing the exact reason why it is, but before we do, we'll do an example. Because I always believe if you do examples, you will be understanding the question better. So let's do an example first. And then the last part of this class will be deriving some inequalities. That will give you more idea.
So if we take when we took that A matrix of M cross N,
yeah.
So that means that there are that space is a m-dimensional space which has n vectors spanning it for the maximum condition.
See, so there are ways to look at it. So if you have AX, right? So let's come to that. Okay, if you still by end of 15 minutes, if you're not clear about it, you again ask me. Okay.
Okay.
Yeah. So because I want to do this example first before I go on to do that. It's just the way I like to do things. So first of all, I will do a row reduced. This is called a row reduced echelon form, which I've already done. We'll do elimination and find out the null space and the column space. So by just seeing this A, can you tell me what is the dimension of the column space or the basis of the column space? Column space of A. Yeah. 3. No, 2. I'll show you why. You could have told me 2 direct. See why?
I didn't see the 2 in the last column.
Yeah. So if you have this, if you see the rows, it is easier here. So you see rows. These two are same, right? So they are dependent, right? Yes or no? And you have one more independent. So 2 independent rows.
Yes.
So that is equal to rank of A.
Yes.
And that is equal to column space of A, dimension of the column space of A. We'll come to why it is true. So column space of A is dimension and row space of A dimension is all the same. And it is equal to rank of the matrix. And we'll see why it is true. Don't be tensed. So once you will do this, you'll understand. So you have 1, 4, 3, 2. 1, 1, 2, 2, 2. So my goal is to now find the null space. So x equal to 0, right? If I have ax equal to 0, do you agree I can do any row elimination again to get? Yes. So this null spaces bx will be the same null space.
Yes.
Very good. So now give me some very nice, insightful row eliminations that will give me understanding of everything. So I will do 2 methods today. One is the method that I have given that is present in the Gilbert Strand book. This is called the row reduced echelon form method. Another is in the Horn and Johnson and other books that I told you. In that one, you will be having this augmented matrix method, which is also very intuitive. But let us start with this. This will give you idea of pivots and all. So tell me what will I do? We have already done elimination. Do intelligent elimination and tell me. Steps are the same.
R3 equal to R3 minus R1 then.
Very good. So remove everything below it. 4 minus 2, 0, right? 3 minus 1, 0, right? And 2, 0, 0. Now, Ritik, will you be able to answer your question? I think you'll be able to answer. So once I do this, do you see? I have already taught you something known as the Jordan elimination, which will be doing reverse, right? So I got this is the first pivot. And this is my now the second pivot. Do I have any more pivots? I don't have anything to reduce below it, right? No more operations. So then I can move on to the next pivot, which is a 0. So this is not a pivot. So zeros cannot be a pivot. Remember that. Okay. In case you get zeros before, if this was 0, you had to move to the right. Okay. If this was 0, you move towards the right and select this as the pivot. 0 can never be pivot. Okay. So you can move like a maze. Start off here, go here, go here. I'm just showing you the. So this way you can select the number of pivots. So what is the number of pivots over here? 2. Yes. So now can I eliminate the terms above also? I'll tell you why I'm eliminating them. Just eliminate them and tell me. So 1, 0, 0, minus 2, 0. And what will this be? I can't calculate. Tell me. So I'm subtracting. Good. Into 2 and then subtracting, right? So into 2 and then, no, rather adding, right? Into 2 and adding. So into 2 and adding will be 3 minus 2 equal to 1. And this will be 2. Right? So now these are my pivots. So I'll make a submatrix with these. Something like this. Right? If I make a submatrix like this, I want to make this I. I'll show you why. So if I make this I, how will I do that? Divide the second row by half, right? Minus half. Yes or no?
Yes.
So what will I get? 1, 0, 0, 1 minus half 0, 2, 1, 0, 0, 0, 0. Yes or no? So now you see I have written it in terms of two matrices. One is known as an I matrix.
Plus half, no?
Plus half. Sorry. So one is an identity matrix and one is a, say, a F matrix, right? And I'm again saying I'm citing Gilbert Strang's book here. So this is a F matrix. So instantly I should be able to tell, I can derive block, what is it said? Block vectors such that I can get 0. Can you tell me how? So if I multiply minus F and I, am I going to get 0, 0? Yes or no? Like I'll show you how to get the minus F and I. It's the vector. You'll get a combination of vectors, right? So minus F into I is minus F plus F into I is 0. So how do I do that? So these are called my dependent vectors. What are these called? Dependent vectors. And these are, or say these are the independent vectors, these are the dependent vectors. So because I can modulate the identity matrix, I'll show you how. So see, so can I write, see, I select this column, right? Right? So if I select this column, in the place of F, I will write this column 1, 0. And I will write F. So let us select this column. I will write that in the place of the I. Yes or no? This was my place of I. These two correspond to the I's and these two correspond to the F's. So, okay. This is some B vector. So B into X. What is it? B into X. What is B into
1
X?
into minus 1 plus half into 0.
So it's minus 1, 1, 0, 0 plus, or rather minus half into 0, 1, 0 plus 1 half 0. Is it equal to 0?
Yes.
Similarly, what will be the other vector? I'll be selecting these two and putting in place of f in this place. So I'll get 0, 1, and then I'll be selecting these two, and I'll be getting 2, 0. Is it matching? So see, both of these vectors, x1 and x2, are vectors in the null space, yes or no?
Yes.
So if you multiply, how am I saying they're in the vectors in the null space? So because bx1 is equal to 0, you have told me now, and bx2 equal to 0, yes or no? So do you agree b into alpha x1 plus beta into x2 is equal to 0?
Yes.
So do you agree that you have a subspace now? Very good. So now alpha x1 plus beta x2 forms the, for all alpha comma beta, forms the null space of A. Now do you see? So it is, what is the dimension of the null space? It is equal to number of independent columns, right? Number of dependent columns. For every dependent column, I can make a new null space, yes or no?
Yes.
So, and number of independent vectors will be equal to rank, yes or no? Equal to number of pivots. Very good. So now do you see, Ritik? So, and this is equal to n minus r. So I have derived one equation, which is dimension of column space of A is equal to plus dimension of null space of A is equal to what? N, right? So I can write dimension of null space of A is equal to n minus r. Yes or no? So now do you get it? Ritik will go to more details, but that will be when we are deriving the formal ones. So once you have a vector, you can do row elimination. So what are the basis vectors for the column space now? Column space 1, 0, 0 and 0, 1, 0.
Yes.
You can have these as basis vectors or select any two independent vectors from the columns. So what do I mean by a column space? I mean when I do AX, which is such that is not equal to 0, AX will belong to the column space, yes or no? And you have to tell me why does it belong to the column space of A? Tell me. I'll complete it at 11:15 today. If you are wanting to leave, you please leave. We'll do some important identities and then you can go. So there are only two identities left and then we'll stop. So each will take 5 minutes. So do you agree? So why is it AX equal belonging to the column space of A? If you understood, tell me. If you have understood this, you will understand the question Ritik asked, that what is it a subspace of? So what is AX according to our definition? A1, A2, dot, 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 AN, right? And you have X1, X2, dot, 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 XN, yes or no?
Yes.
So this is equal to what? AI, XI, right?
Yes.
So what am I taking a linear combination of?
X1, X2, Xn.
Exactly, I'm taking the linear combination of columns, isn't it?
Yeah.
So any vector matrix product is a linear combination of columns. So this should belong to the column space of A or not, which is the span given by the columns of A, right? Now tell me what was your question. Now is it clear?
Yes, it is here. Like in this, you can clearly see that because the row becomes 0, the last row, it is clearly two-dimensional space.
Yeah, exactly. So it's a two-dimensional space. So with only these two, you are going to get it. So when you are multiplying AX at, you will get a R rank dimensional subspace. Understood? So
Yes,
AX dimension
rank
of,
will, and the rank will
exactly,
be equal to the dimension because
number of
there
independent
will be,
columns.
yeah, there will be dependent vectors
Yes,
if the rows are more. I mean, if the
exactly.
columns are more. Sorry.
If the columns are more, there will be, of course, dependent vectors. In two-dimensional space, you cannot have more than two vectors, right?
Yeah.
So exactly. So I will give you a homework here. So probably this will be your assignment, not your assignment. So please discuss it in the group. So homework is, so what about solutions to AX equal to B? If anybody is interested, I see a lot of people are. If you share your solutions, I will be sharing a comprehensive write-up of showing you how different they are. So you have to see the null space and say. So for AX equal to B, do you agree if there is a null space and there is a particular solution such that AY equal to B, there are infinite solutions? I'll just give you the hint. Say there exists a space, say there exists X such that AX is equal to 0, right? And AY is equal to B, right? I need to solve for this equation. Solution to initial problem statement. So this is the problem statement, is your homework. So how many solutions will you have for this? So hint I'm going to give you using the null space thing. Yeah. So if there is a particular solution, AY equal to B, say Y you know, already know, and you can find the null space of a vector now, right? Can you find a null space? I have shown you how to find it. Say it's not full rank, then you will have null space or not. So you're something like this. I'll give you an example. So if you have more equations, more variables, x1, x2, xn, say x1, x2, xn, and you have say 3 equations and 7 unknowns. M is less than n. So then what will happen? Say it is full row rank. So you have full row rank, all the pivots, right? So what will be the dimension of your null space?
And
Null space. So you have a is equal to, or let us stop here only. We'll do the equation, these identities next day. I don't want to rush them because next day anyway there's a shorter class. Okay. So you have x1, x2, xm, right? So rather write p1, pivot 1, pivot 2, and pivot m. So what is the dimension rank of this matrix? At most, what can be the rank if m is less than n? Let's do it.
M.
Yes. I will do it here, then you will understand. Say you have equations like this: x1 plus x2 plus say a1 x1, a2 x2, an xn is equal to b1, a21 x1, a22 x2 dot dot dot, a2n xn. Let's take a concrete example: 100 equal to b2, and all the way to a21 x1, A21 1x1, A22 21 2x2, and so on. TA 21 n, which is 100. X 100, right? So how many equations do you have here? So you have to give me the complete picture of where m is less than n is less. So your homework I'll tell you after this. So say here, do you agree m is less than n? So your matrix will be something like this, right? A11 till A1n. It will be something like this or not? AM1 till AMN, right?
Yes.
Where m is less than n and m is. So what can rank be at most? It's a m cross n matrix. So m is, to answer your question, I'm doing this more. So m is less than n and this is the rank, right? Agreed?
Yes.
So I'm saying this is the case 1. So can you tell me how many solutions will I have to this equation? To B.
M minus.
So there is a very easy solution. Like if you can just see it, you will be like, wow, I have done it. So do you see that here from here to here? This is a m by m cross m matrix or not? And you have how many columns left?
M minus M.
M minus
N
M.
minus M.
N minus m. So this will be your dimension of null space, right?
Yes.
Very good. So if this is your dimension of the null space, and so this is your dimension of R equal to M is your dimension of the column space. Agreed? So there are your column space is A dimensional. And similarly, your B is also a M dimensional column space.
It will be M dimension M number of solutions.
Yeah, exactly, you're going in the right direction. But let us see. So is B a M dimensional vector or not? So you'll be multiplying this with a x1 dot 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 xm plus 1 to xn. Yes or no?
Xn plus 1 to xn will be 0.
Exactly. Very good. So if I put all these to 0 for the time being, I can solve for this equation a tilde times x1 to xm. I will have one solution. Tell everyone to see this. This explanation is not also there in any Gilbert-Stein sessions also. So this I will put to 0. So this will become x equal to b, right? So that man has, if you see his videos also, you'll also like, you'll understand so nicely he teaches. So that's why he's the first person who taught me this. So then I learned from IISc and all. So I'm trying to incorporate everything into your session. So you will have a solution or not? Say a y solution. Y is equal to x, m, and 0. Agreed?
Yes.
Thus that ay equal to b. Now, will you also have a null space of this matrix?
Yes, I will.
How many dimensional null space?
N minus M.
Correct. So you will have ax equal to 0, where x will belong to a n minus m dimensional null space. This is called a particular solution. So I think you have done this in your differential equation. Same thing. Differential equations can also be solved using linear algebra. I'll give you one example later. Particular solution. Right? This is a particular solution. And this is your homogeneous solution.
Oh.
What Hebrew am I speaking? Now let's see. Let's see what Hebrew am I speaking. So if x belongs to null space of A, right? Do you agree that y plus cx will be equal to b. Yes or no? So because ay is equal to b and acx is equal to 0.
Oh.
So your solution space, this is, if you have not understood it all this while, will be your x cap, which is the solution, will be, this is why in your school books it was written, if there are more number of unknowns than equations, there can be infinite solutions. But remember, there can be 0 solutions also. This is a trick question I'll give you. Okay, so C into, yes, you will see. You have to do it yourself. I'll give you a hint. I'll give you, so this case you understood, right? Where m is less than n equal to r, right?
Yes.
So your homework would be, now Ritik, do you understand all the spaces clearly?
Yeah, essentially, like this A space, A vector space was divided into two parts, which is X and Y. And the
Exactly. So
sum of X and Y will become A.
yes. So, and you can always divide a matrix into two different subspaces. One would be around the columns, along one would be along the rows. And all of that depends on if you are doing a AX multiplication or A transpose X multiplication, right?
Yes.
And others, Brahmojit? Okay. So your homework would be, how many solutions? Solutions. So easiest case is m equal to n equal to r. We have already done unique solution, right? So I will not, you don't need to do this, right? Second question is n greater than, or I will give you this as your assignment question only. Two assignment question I will give you. You keep it ready. I've been telling you from beforehand. It will be your assignment question. N, don't post it. Your n is less than m. M is greater, so you have more columns, and where this is equal to r, right? And number 3 would be a case where you have a matrix like this, where n is n is greater than m. Again, number of equations, but r will be even lesser. Right? You can think of a matrix like this or not. Can you give me an example and solve solution you can do at home?
The example we just did.
Exactly. Very good. Example we just did. That's why I took this example. I constructed this in my head. Where is the example?
The two common rows one.
Yes, here. So do you agree? In this case, your m is equal to 3, n is equal to 4, rank equal to 2. And if you have some ax equal to b, you think what will happen? In your school books, this case was not given. This was omitted. So there can be many. So just think. If there is a b, instead of here, just we found the null space. If there was a b, what you would do? So the last thing we'll do is the augmented matrix method, and we'll stop. We'll not do the inequalities today. We'll do it tomorrow in the first part. So using augmented matrix, so we have found column space of A, found null space of A, found now column space of A transpose, and null space of A transpose is left. Let's do it. Let's copy this. 1432. Can somebody dictate to me? It's very dirty, so I don't want to copy it. If you have noted it down somewhere. A is equal to 1432.
1 2 2 2 1 4 3 2.
1 4 3 2.
3 2.
So now you tell me, if I have something like this, again I will be using that thing that I have used all this while, right? If I do something like this, the augmented matrix, what will my goal here would be to get a row reduced echelon form in the first case, yes or no? And some zeros below that we got when we were doing the elimination, yes or no? Here we got that, right? So we'll get something. So this is called a row reduced echelon form. This is called a row reduced echelon. What does an echelon mean? All the people who are very good in English. An echelon is a stair. So you see, you will be going only like this, right? As I told you, isn't it? You'll go like a stair, so that's why it's called a row reduced echelon form. You're reducing the row into an echelon form. So you had some zeros at the end and some triangle some matrix on the top, right? Upper triangular, whatever you are doing, doesn't matter. Yes or no? Okay, once I write, you will understand. So if I do this elimination, I get some thing here. I get some star over here, and I get, say this is, how many dimension will these zeros be? Can you tell me? How many dimension will U be? Yeah, Ritik, tell me. You can tell me. So this is
n minus 1.
no. There are many zeros here. It's a zero matrix, not a zero vector. So it's something.
It will be lower. Triangle will be 0, no?
Yeah. So it is not. It is two box matrix. This is one matrix. This is one matrix. Right. This is a zero. I'll give you an example. So 1, 2, 3.
M minus rank.
Very good. So it can, this zero means this zero. So this is, do you agree that this is equal to the rank? You can't do any more elimination, right? Number of rank will be equal to number of rows in U. Yes or no? Rank of A will be number of rows in U or not?
Yes.
Correct. So this is R dimensional. So what will this be? M minus R, right? So you will have P1, P2, dot, Pm minus R. So do you agree these will be the null space of A transpose? And you will ask me why. I will tell you, because when I did row operations like this, I did some row operations, right? Corresponding to these rows, whatever row operations I did, X transpose A, I got 0, right? Yes or no? Corresponding to all these rows, whatever row operations I did, I got 0 or not?
Yes.
So what will happen to the identity matrix? Won't I get the x's here, x1s, x2s, and xm minus r? If it is x1, x2 transpose A, dot, x m minus r transpose A, this is equal to 0. So what will I get in if it is identity matrix? So I will get x1 transpose, x2 transpose, dot, x m minus r transpose, right? Yes or no? So in this part of the matrix, augmented matrix, you will have all the null space of A transpose. So see, this way also you can do a simpler version. This is a simpler way to do the same problem. In the same augmented matrix, you will be getting the null space of A transpose and also the row space of A. Row space of A. I'll show you with this example, it will be very clear if it is not clear abstractly. So what will I augment the matrix with? 1, 1, 1, 4, 2, 4, 3, 2, 3, 2, 2, 2. What will I augment it with? An identity matrix, right? Just as we did. Am I audible?
Yes.
So 1, 1, 1, right?
Hmm.
So next, what will I do? I will do row reduction again.
Yes.
So what will this matrix turn out to be? 1, 0, 0, 4 minus 2, 0, 3 minus 1, 0, 2, 0, 0, 1 minus 1 minus 1, 0, 1, 0, 0, 0, 1. Yes or no?
Yes.
Now you see, immediately you get a 0 here, a 0 row.
Hmm.
How many columns are there here? How many rows are here?
2.
2, and they're independent or not? Can you make it more zeros? Can you get independent? So these are your row space ka. So these are basis of row space or not?
Yes, basis of row space.
Basis of the row space or the column space of A transpose. Yes or no?
Yes.
Similarly, this will be your element of the null space of A transpose. Do you see why? So see, multiply minus 1, 0, 1 with 1, 4, 3, 2, 1, 2, 2, 2, 1, 4, 3, 2. This is what I was meaning by doing all these operations over here. See this part? That's what I was meaning. So aren't you getting a 0? You're getting a 0, right? Ritik?
Yes.
Ritik and Brahmali.
Yes.
So what did we understand? That if we do a elimination on this type of a matrix, I will be getting U zeros star and null space of A transpose. So here I will get the row space. Here I will get the already I've written. So can I use the same method for my column space of A? For column space of A, what will I do? If you have understood. So this way I found row space and null space of A. If I have to find the column space and null space of A, what will I do?
Transpose of A.
Exactly, finished. So if you take A transpose and augment it with AI, what will you get? Rather this way. And you will multiply E on the right. You will do column operations. So then you'll be left with
Column
basically
space 0
exact.
and null space of A.
So you'll be left with U 0. Corresponding to this, you'll have some star, and corresponding this to this, you will have null space of A. Right? Agreed?
Yes.
So basically, if you have A, you convert it into A transpose, and you can still do the same operations. Nobody will stop you. For the row space, it's simpler to understand. For the column space, if you work out an example, do the same example yourself, you will understand. Okay. So with that, we'll end today. So tomorrow, do you want to have a evening session around 3, or do you want to have it from 10? 3 would be better, right? Just now finishing, and then you need to sleep also.
Yes, I think 3 is better.
3 or 3:30, something like that. 3 is better. We'll complete by 5:30. The only reason I want to, I am taking these classes one after the other is one thing. I will from the middle of August. So let me stop recording. I don't want it to be on YouTube. I don't want to